record it. So it's on and recording. Let's see. There's Steffi and Kessa. We'll give folks a couple more minutes. I got my office back. Got the doors put in yesterday. And now the cat litter boxes are back where they're supposed to be.
What kind of doors did you get?
Exterior doors, one just plain with a half window. And the other one was an atrium door. So half of it is fixed and the other half is a door. And they're both full-length glass.
Ooh.
With the blinds that are inside. So now the cats can't tear them up.
That's a blessing. I know all about that.
So I'm trying a new. Oh, got another. There's Isaac. There, I see him. Isaac is present. Okay. 3 down. We have a quorum. The only problem with teaching this way is my whiteboard is kind of small. So I might have to write a little bit and then erase some and write and erase. Fortunately, it's recorded. Okay. Anybody had a chance to read chapter 10 yet? I see a nod. Okay. That's good. See a couple of nods. Even if you just skim through it once, it'll give you an orientation. Let's put it that way, orientation in the material. And then we go into more detail during the lecture. Okay. You haven't heard from Megan, have you?
She's trying to get on. She's trying to get on Zoom right now. She's having trouble with it.
Oh.
Yeah, but she's on my phone. She's here. She's trying to get it fixed.
I give her a half check.
He'll give you a half check because you're on my phone until you get on Zoom. So you're present but not present.
Is she trying to get on her phone or on her laptop or computer?
On her laptop.
Okay.
It's opening right now.
I'm sorry?
She said it's opening right now.
Okay, that's good. I got to do something about this phone. Ah. Okay. You still there? I want Medicare Plus card. My callback number is 866-201-7894. All right. Megan gets a hold check. Let's see if I can cut the volume out of this thing. Only other option is to unplug it. Calls will not be answered. There we go. Okay, we just need Heather now and we'll be a full group. So Steffi tells me that the video that I produced on the intro is visible and you can read stuff in it. So Megan, you can go back and look at the intro. A lot of that stuff you've seen before, but since the lab is going to be delivered solely by the web, you may want to take a closer look at that. It's the last half of the video. And that way you'll get some orientation. Well, I think we better jump into chapter 10 and see if Heather comes along later. Let's see. Yeah, there's nobody there waiting. Okay. So first thing you need to do is if you haven't already set it up, well, everybody set it here. There she is. All right, that's everybody. Okay, Megan, what we had done was learned how to split the screen in a side-by-side mode so that you can see me and the whiteboard on one half and the PowerPoints on the other half. And the way to do that automatically is to go to your profile picture in the upper right-hand corner and go in the profile, and there's a switch for automatic side-by-side. And if we've already started, then you can do it manually. I'm trying to remember where that is. Since the host doesn't have an option to do side-by-side, that would be ideal, but a glitch in the program, I guess. I guess I could look at the document, wherever I put it. These instructions, Megan, are in the syllabus also. All right, so automatic, here we go. Let's see, view options. So wherever your view options are, of course, I'll have to share a screen before it'll work. So let me do that. Let me call up, I should have already had these ready. Let me call up the PowerPoints and share them. Let's see. Go. Okay. Now let me see. I'm not sure which to do first. Share it and then start the show, or show and then share. But I'm going to try sharing first. Okay. All right. So there's chapter 10. Let me see if I can start the show. There we go. Okay, so there should be an option if you're not set up for automatic view options. I don't even see it on mine. You guys must have it on yours. Got to back up. There we go. Okay. I lost Megan. There she is. There you are. Megan, do you have side by side now? You just give me a thumbs up.
Yeah, I do.
Okay, good. Excellent. Okay, so now we can get started with the material. All right, first exam is going to be on this chapter and chapter 11. And I'm going to reduce that so I can see what I'm doing. There we go. And that's okay. All right, chapter 10 is on liquids and solids. So when we think about liquids and solids, or any matter for that, for our purposes, is we have to think in terms of bonding. What is holding the individual components of the liquid, solid, or the gas for that matter, together? What makes them hold together? There are two types of bonds. The intramolecular bond is the one that actually holds the molecule together. And for bona fide molecules, by definition, their bonding is covalent. It's very strong. It's the strongest bond between atoms. It holds a molecule together, and the molecule behaves as a single unit in that liquid or solid. And then the other type of bond is the one that holds those molecules together in that particular phase. These are intermolecular forces, and they are necessarily weaker than the bonds that hold the molecule together. It just makes sense. If the intramolecular bonds were equal to or even weaker than the intermolecular bonds, then they just tear apart at any given temperature. So the intramolecular bonds are the stronger ones. The intermolecular bonds are the ones we're interested in determining what phase the substance is in. And they fall into, actually bonds themselves fall into several categories. We just talked about one, the sharing electrons, the covalent bonds. There are also ionic bonds, right? We're not going to discuss those yet because the ionic bonds don't give you molecules. They give you a crystal lattice. So we're not interested in those just now. We're more interested in those that have molecules and the bonds that hold them together. So then the next weakest bond is the dipole-dipole bond. When we talk about dipoles, when you think of a pole, think of a magnet. Right? A magnet has a north and a south pole. And if you bring two magnets together, the north poles will repel each other, but if there's a north and south pole close, they will attract. So for molecules, it's not quite like that. It's not magnetic, but it is electrostatic. And a molecule that has, let's see, let's use a real simple one, like this. Hydrogen fluoride. Okay. Remember when we discussed in first semester the periodic trends of the periodic table, the trends in senior moment. God, I hate it when that happens. Anyway, I'll think of it in a second. But it has to do with the pull of electrons for each atom. And the fluoride has a electronegativity. Thank you. The stronger electronegativity is with fluorine. than for hydrogen. So even though this is a covalent bond, the electrons tend to spend more time with fluorine. So we get a slight negative charge toward the fluorine and a slight positive charge toward the hydrogen. Now that's not a complete charge, right? A complete charge would be a total transfer of electrons, one or more, to the other atom. Then you've got ionic bonding. We're not talking about that. This is still a covalent bond. It's just polar in the fact that the electron distribution is heavier on the fluorine side than on the hydrogen side. So that gives the whole molecule a polar character, right? So it's going to be slightly negative here, slightly positive there, and that's what that little delta means. It just means slight, a slight charge. So what happens when you get a large collection of these atoms in a substance, hydrogen fluorine gas or hydrogen fluoride gas? What they'll tend to do is orient themselves so that the slight positive is lined up with a slight negative, right? So this characteristic is called a dipole, and we sometimes we indicate the dipole with this symbol, right? So this shows the positive side, and this points toward the electron density. The increase in electron density is that direction, right? So now that we know the dipole of the atom, the molecule, they will orient themselves to attract negative to positive and form a slight attraction. Now this attraction is much, much weaker than a covalent bond. It's even weaker, well, it's definitely weaker than an ionic bond. But it does explain why liquids exist and solids exist under certain conditions. And for the most part, we're talking about temperature. How much energy are you putting into the system? Put a lot of energy into the system, then you increase the vibrational energy of each atom, and it tends to break those bonds. So if you break those bonds in a solid, they separate and they can move around, and you get a liquid. If you add enough energy, if you increase the temperature high enough, then you break the bond in such a way that they virtually separate from one another and do not experience any dipole-dipole interaction. Okay, you can interrupt me anytime, right? Just like we were in face-to-face. So that's the dipole-dipole interaction. Weaker than a covalent, weaker than an ionic, but strong enough to account for differences in phase. There's a special type of dipole called the hydrogen bond, and this is one example of that, where you have a highly electronegative atom linked to a hydrogen, covalently linked to a hydrogen, and anytime the hydrogen positive, slight positive, interacts with the slight negative of another molecule, you get that hydrogen bond. And you can think of it as a spectrum of energy spectrum, right? So more energy is this way, less energy is this way to break the bonds. So for the dipole-dipole interactions, the hydrogen bonds are way out here. They are the strongest dipole-dipole interactions. And then you have progressively weaker depending on the difference in electronegativities. A good example of hydrogen bonding has to do with water. You have oxygen bound to two hydrogens, gives you a slight distribution of negative charges toward the oxygen. See, I'm already running out of space. Right, so you get a slight positive here, slight positive here, and a slight negative there. Of course, to balance those two, we better make it 2. Now, the bonds themselves are polar. And if you take them together, the molecule is also polar. We'll talk about that in more detail later. But when these molecules come together, because you have an electronegative atom here and a hydrogen there, you get the possibility for hydrogen bonding. That's why water is a liquid at 1 atmosphere pressure and normal surface Earth temperatures. It's liquid. If it were not for this hydrogen bonding, all the water on Earth would be a gas, and we'd be in huge trouble. Okay. So what if we don't have dipoles? Now, before I move on, you can get a molecule with a dipole interacting with ions, right? Because all you need is that difference in charge, the negative positive, and you can get an interaction. So the dipole ion interaction is also positive. But suppose you have a molecule that has no dipole. Like nitrogen gas, right? The bond between those two nitrogens is extremely strong, very strong. But since you've got two nitrogens with identical electronegativities, the distribution of electrons in this molecule is virtually uniform, you would think. But we do know that at 20 degrees centigrade, nitrogen is a gas. But at minus 195 degrees centigrade, it turns to a liquid. Now, the only thing that can explain going from a gas to liquid is there's something bonding those molecules together. Only we haven't explained it yet. So we need an explanation for why this would bond with another dinitrogen. So that's where London dispersion forces come in. Talk about weak. We know they're extremely weak because we have to cool nitrogen down so low in temperature before they become effective. Now, I might also add that dipole interactions and London dispersion forces are always there. And I'm going to explain what they are in a second. But if you have dipoles also in that molecule, they're so much larger that the London dispersion forces are insignificant. Right? They don't count. They're like the 10th decimal place error. So what is the London dispersion force? Well, when we say dispersion, we're talking about dispersion of charge. Right? So instantaneous redistribution of charge is a premise for London dispersion. So as these electrons are in rapid motion, you might say, sometimes they tend to collect over here maybe. Well, if they do that, that leaves this one with a slight positive charge, right? And I'm talking about very slight. But it only happens for an instant. But that instant is long enough to induce a redistribution of charge in a neighboring molecule. So if we have another nitrogen over here, then that negative is going to repel electrons from this side of the molecule, and they're going to end up over here. Oops. So for an instant, and I'm talking about picoseconds, you have an unbalanced charge in the molecules, and you get an attraction. If there's enough energy in the system, then the bond is not strong enough to hold them together. That's why we have to get it really, really cold, reduce the energy of the system before it will liquefy. You can think of that in terms of other molecules also. Right? For instance, carbon dioxide. Everybody knows dry ice, right? So carbon dioxide, right, looks like that. I'm going to leave out the lone pair electrons just for simplicity's sake. So that's a symmetrical molecule, and oxygen is more electronegative than carbon. So the bonds themselves are polar, right? You get a dipole that direction and a dipole this direction for the bonds. But since they're pulling in opposite directions, they cancel one another out. So the whole molecule is nonpolar. But those bonds, you still have that distribution, right? Negative, negative, and positive. And on top of that, you do have some London dispersion. But to illustrate the difference in the strength of the bond, remember nitrogen liquefies at minus 195 centigrade. That's for dinitrogen liquid. Carbon dioxide solidifies at minus 78.5. Right? So that's a solid. So you can see, based on this evidence alone, in support of the theory, of course, the attraction for one carbon dioxide molecule to another is much stronger than one nitrogen molecule to another. And this is evidence for it. The freezing point or liquefaction point. Okay, any questions? I spent a lot of time on those, but I thought it was important to get those basics out of the way. And there are probably subsequent slides that are going to rehash that too. You know me, stream of consciousness. Whoop, wrong button. Let's see. Space, there we go. So there's our hydrogen bonding in water. And these dots here are what we use to represent the hydrogen bond. Okay, so we can move on from there. All right, so this is just the usual concept check. Which is stronger, the intramolecular or the intermolecular? The one that holds the molecule together, right? The intramolecular is a stronger set, a stronger bond in general. Of course, you have a spectrum of strengths of bonds. And how do we know that? Well, I mentioned that earlier. The intermolecular bonds are responsible for phase changes because the molecules have to hold together. If we break the intermolecular bonds, then we have a chemical change. And now we don't have that molecule anymore. So the intramolecular bonds have to be stronger to hold a molecule together in the processes of phase changes or any other type of physical change that they may undergo. Okay, just hammering the point. When a substance changes from solid to liquid, the molecules always remain intact, right? And we know that because we can freeze water, we can boil water, and we can convert it from one form to another, and we still have water. Now, these dipoles that I mentioned earlier, the illustrations that I was using are for simple molecules. But when you get to the point where you're studying very large molecules, polymers, biochemicals like proteins and polysaccharides and those, when you get to those huge molecules, you can have differences in dipoles at one end of the molecule from the other, right? And when that happens, sometimes those molecules can turn around on each other and interact intramolecularly. It's kind of interesting, but a little beyond our topic for the present. I just wanted to point that out. Okay, so this is just an illustration of what you see in solids, liquids, and gases. The big difference is gases, there's lots of space between them. Remember, that's why a gas mixed with a gas always makes a solution. There's lots of room and very little interaction. In fact, the interaction of one gas molecule with another one, we can assume is like billiard balls. They just bounce off one another. That goes back to the kinetic molecular theory of gases that we studied in gases were chapter 5. Now, when you get to liquids and solids, then the intermolecular forces become more significant and happen at, of course, lower temperatures, right? If we have higher temperatures, then there's enough energy to break those bonds, so we have to lower the temperature. And for the liquids, they're pretty much amorphous. In fact, they are amorphous. In other words, there's no structure at all to a liquid. When you get to a solid, you can have amorphous solids, but some solids regularly arrange their molecules in a crystal lattice of some kind. And it doesn't have to be ionic to be a crystal lattice. We can make a crystal lattice out of a molecular substance. In fact, that's what was required for Watson and Crick. Actually, their female assistant did the work to crystallize DNA so that they could use X-ray diffraction upon the molecule. They had to find a way to crystallize it, and it wasn't ionic, right? But they had to. It had to be done. Otherwise, they couldn't use that technique. Okay, so we'll talk about liquids and solids more as we go along. So as we change from a solid to liquid, we add energy, motion increases with the energy, and it reaches a point where it breaks the bonds that hold that solid together. Now the molecules are able to move freely past one another, but they still interact. They interact enough to hold them in the liquid state. It doesn't hold them strongly enough to maintain a shape, right? They assume the shape of the vessel, but it does hold them strongly enough to maintain their volume. So now we're getting an indication as to why solids are classified this way, liquids are classified another way with these characteristics, and gases as well. It has to do with those intermolecular bonds. Okay, and this is just another illustration. You see that let's see if I can get my pointer in here. You see the densities of the solid and liquid. Normally, the solid would be more dense than the liquid. But there are some solids like water that defy the rules. And the reason for that is when water, when we lower the temperature enough, 0 degrees at 1 atmosphere, the water starts orienting itself positive to negative dipole, that interaction, but it does so in a regular crystal structure. And whereas you have water molecules all along like that in the liquid state, and they could interact anyway. They could be anywhere. With a solid, they tend to arrange themselves in 6-sided structures, in hexagons. Okay. So you get another oxygen here, another oxygen here, 1, 2, 3, 4, 5, 6. So that's not right. You have like that. Right, so you get that hexagonal structure, and notice that what happens in a hexagon there's lots of empty space in the middle that wasn't there before. So that's why the density of the solid water or ice is less than it is for the liquid, because it just tends to do like that and lock in place, and all that empty space in the middle has to be accounted for in the density, and that's what decreases the density. Evidence for that, look at any snowflake. You know, how many points on a snowflake? It's always 6. Even though every snowflake is unique, it's always got 6 points or 6 sides. Okay. So I've already talked about this, I think, in nauseating detail. The dipole-dipole forces are occur between molecules that have a polarity, right? The bonds have to be polar, and sometimes the molecule is also polar, but the molecule could be nonpolar and still have those polar bonds. When we talk about polarity, actually there are 2 ways of describing polarity. I think there are 2 or more slides later that cover this, but seems like the appropriate time to discuss it. When we talk about polarity, you have polarity of bonds, and you have polarity of molecules. Right? So we have to consider both when we're discussing intermolecular interactions. If you're going to have dipole-dipole interactions, you have to have polar bonds. But you can also explain part of the way that molecules interact with the overall polarity of the molecule, right? So with carbon dioxide, we have those polar bonds, but they canceled one another out. So what that did was it reduced the polarity of the individual bonds by their interactions within the molecule, right? So illustrate like that. Carbon dioxide, and then there's carbon monoxide. So you have similar, not exactly the same, but similar bonds. You have carbon and oxygen here interacting. So these are going to be slightly negative. That will be positive. This will be slightly positive, and that will be negative. Right? So when we look at the physical traits or measurements for this molecule versus that molecule, you would expect that the freezing point for this one would be lower than for this one, because you have not only a polar bond, but a polar molecule. So you should see this one freeze at a higher temperature. Rather than 78.5 degrees, it should be something much higher, maybe minus 50 or minus 40 degrees. You should be able to change phase with this one. Okay, does that make sense? I hope. So when you're describing, here's good, if you encounter a question on a test, all right, and it says, is this molecule polar, right? Well, first of all, you have to look at the bonds. Are the bonds polar, right? If the bonds aren't polar, you stop there. Right? And the molecule is nonpolar. But if the bonds are polar, then you look at the molecule. Now, what determines the polarity of the molecule? the shape. Right? If it's linear, like carbon dioxide, then if you have the same polarity of bonds on either side, they cancel one another out. But if you have polar bonds like in water, water is bent, right? And our VSEPR model says that the electronic structure for water is a tetrahedron, right? Because you have two lone pairs. But the molecular structure of water is bent, right? So that's what gives the overall molecule a dipole moment in that direction, right? Because these two bonds actually add together in their positive nature and the negative nature. So that gives you a polar molecule as well. Okay. That just means when we get to those slides later on, I can skip over them. Okay. So those are dipole-dipole forces between molecules that have molecular character, not ionic, but molecular.
Bonds between atoms with different electronegativities have a...
Can you hear that? Everybody hear that? Okay, good, good.
Have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules such as sulfur dioxide are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
Okay. She said it more succinctly than I did. She took about, I don't know, 2.5 minutes. It took me 45. Okay. Oh, we got another one.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with 2 hydrogen atoms and 2 unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
Okay. I had to answer the door. My cat was knocking. I've got a door banger. When he wants in a room, he knows how to reach under the door and pull it and bang it. So Every morning, he's the one that's elected to wake me up to feed everybody. Okay. That's hydrogen bonding. And normally, let me see. Can you see this periodic table? Let me get a little closer. Hydrogen bonding is generally due to bonds from hydrogen with either fluorine, oxygen, or sulfur. In those cases, the electronegativity difference is enough that gives you that extra strength, character, ionic, dipole character in the bond. Okay. So, well, what did I say? I said sulfur, nitrogen. I think sulfur counts also. They only, the authors only consider nitrogen, oxygen, and fluorine. But I think sulfur should also be in there. We can argue over that some other time.
In solid carbon dioxide, dry ice, nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
Okay. London dispersion forces become larger aggregate and more significant as the size of the molecule increases, because you have the opportunity for greater separation of charge from one end to the other. That's why there's a series of hydrocarbons. Right? You can have methane is the simplest, carbon and hydrogen. Then you have ethane, propane. Right? The molecules are getting bigger, but all they have is carbon and hydrogen in a chain. Right? This is called an aliphatic series. So you can get up to very large molecules. I think when you start getting into diesel fuel, you're talking about 10 or larger. So these molecules are very large, and that means that their London dispersion forces can be distributed all over that molecule. You could have positive, negative, positive, negative, positive, negative, all down the molecule. And since they're linear, they're able to line up with each other, right alongside. So you get an aggregate increase in the attraction of these molecules. That's why methane, ethane, and propane are all gases at room temperature. Butane is too. Pentane is a liquid, right? And then 6 is hexane, then heptane, octane in your gas tank is a liquid. And you get up to the point where you get diesel. Anybody who's used a diesel engine knows that diesel fuel is a lot thicker. I mean, it's more viscous than gasoline. And then you get to the point where you run into very large molecules, and you have asphalt, right? So those molecules are solid. That's why they use them to hold aggregate together on new construction of highways, like is happening out here on the turnpike between, let's see, between the split of 6477 on up to, let's see, Route 19, I think is where it branches off. So they're using asphalt, and it's a solid because of these London dispersion forces. Okay. Like I said before, London dispersion forces occur in all molecules. But if there are other forces that are stronger, they become insignificant. Melting and boiling points, they are a direct result of intermolecular forces, right? So if you know you have two molecules, one has a boiling point that's here, and one has a boiling point that's here, you know that the stronger intermolecular forces will be found for this molecule with a higher boiling point. It takes more energy to break those bonds. Okay. Melting point, the same thing. A higher melting point means the bonds are stronger between molecules, or actually among molecules, since there's more than two usually. Okay, this is just an illustration of the different hydrides of elements from the periodic table. And what you see is the boiling points increase. Let's take this bottom list here. Let's see, over here, right there. I probably ought to change my cursor maybe to a dark cursor. I'll do that later. So if we go from carbon, silicon, germanium, and tin on the periodic table, let's see, there you go. There's carbon, silicon, germanium, tin. So the carbons are getting bigger. I mean, the atoms are getting bigger. The central atom is getting bigger. And the electronegativities are changing, decreasing a little bit as you go this way, right? But since the atoms are bigger and consequently the molecule is bigger, the London dispersion forces become more significant. Remember what I said about size. The larger the molecule, actually the larger the atom, the more significant are the London dispersion forces. You can see that trend. Let's step away from this chart for just a moment. You can see that trend with noble gases, right? So the noble gases, as you move down, they get bigger, and their boiling points also decrease. It takes less energy. No, their boiling points increase. Excuse me, they increase because there are more significant London dispersion forces among molecules as you decrease, go down and increase in size, because the opportunity for dispersion of electrons around a larger atom are greater. So you get more forces down here, and it takes more energy to boil them. Yeah, that's a good term. Okay, so let's go back to the chart. So we see this trend. The boiling point increases as we increase the size of the central atom, okay? The problem, and that holds true for the third, fourth, and fifth periods, right, for all the hydrides. But when you decrease the size and increase the electronegativity, you start getting into the realm of hydrogen bonding, the significant dipole-dipole interactions, and you get polar molecules. So we've got two things going on here. Is your molecule polar? In which, well, with all the, in the carbon family, they're all symmetrical molecules, right? So the only difference there is the London dispersion forces. But as you move into, move to their neighbors, like the pnictogens, of the nitrogen family, and the halogens, and the chalcogens, oxygens, you get that polarity that overrides at least for oxygen, fluorine, and nitrogen, that polarity overrides the London dispersion forces. You get the hydrogen bonding. So that's why you see that discrepancy. Let's see, where's my pointer? See that discrepancy here. But once you get up into this region, the London dispersion forces become more significant as the molecules increase in size and the polarity of the bonds decrease. Okay, that's the only point I wanted to make out of that chart. So let's see if we learned anything. Which molecule is capable of forming a stronger intermolecular force? Well, you look at the polarity, right? So you would expect, since nitrogen is nonpolar and water is polar, that the stronger intermolecular forces would be among water molecules. Okay? And there's a short explanation if you want to look at it later. All right, hopefully you've already printed this out. Okay. This is an illustration of two molecules that have identical molecular formulas, C2H6O. And their only difference is that they are isomers of one another, structural isomers. That is, they have a different arrangement of atoms, but they have the same number of each of the atoms in the molecule. So what you see is with this one on the left, C2, actually C2H5OH would be ethanol, the drinking kind. So what this gives you is a hydrogen bonding portion of the molecule over here, right there. Whereas this one, with the same formula, is dimethyl ether. And it's symmetrical in such a way that the dipoles cancel out. Actually, it does have a slight dipole. And the reason I say that is because the central atom is oxygen. It has these two lone pairs. So the electronic structure, according to the VSEPR model, is tetrahedral around that oxygen, right? So it should be a bent molecule at the oxygen. So you would get some dipole, some polarity in that molecule, but you would not get nearly as much to give you the type of bonding that you would experience with ethanol. Okay, those are the significant differences between these two molecules, has to do solely with their structures. Okay. So what do we mean by a gas that behaves ideally? Remember what conditions favor ideal gas behavior? High temperature, low pressure. Okay. So in order for that to happen, ideal behavior, you would need, well, there's also another condition. Let me go back to chapter 5. For the kinetic molecular theory of gases, one of the presumptions is that molecules do not interact. They act like billiard balls. They just bounce off one another, right? We know that's not true, but that's the characteristic of ideal behavior, is not non-interaction. So which would be the least likely to interact? The nonpolar molecule, right? So the dinitrogen molecule is definitely nonpolar. And carbon monoxide has a polar character. So you would expect dinitrogen to behave more ideally, in the sense that the molecules do not significantly interact when they encounter one another. Okay? And there's your explanation. Okay. So let's rehash some characteristics of liquids and solids and see if we can relate them to these intermolecular bonds. All right, we know that liquids have low compressibility, right? That's because they're already close enough. If you try to push them together, they don't want to go together. But they lack rigidity, which means the bonds between the molecules are not strong enough to hold them in a fixed structure as they would if they were solid. They have generally high density as compared to gases, and particularly compared to the gas of the gas phase of that given molecule. Now, as another characteristic that we haven't talked about much at all, actually, is surface tension. What do we mean by surface tension? Surface tension can be measured, and it's a measure of the resistance of the liquid to increase its surface area, which means there are forces involved that are holding the liquid together at its surface. Now, why they're there? If we look at the surface of a liquid, you have molecules all through the liquid. And I'm using circles just for simplicity's sake. And they're interacting with one another, right? So they don't, excuse me, be consistent. A line means a bond. So they're interacting with one another. They're interacting all around, right? So theoretically, the forces of attraction between molecules in the body of the liquid are balanced, right? So they're feeling pulls from all directions. At the surface, they're only feeling pulls from molecules to either side and below, right? So what happens is there's a certain amount of, this is the way I rationalize it, there's a certain amount of force that any one of these molecules in the body of the liquid will be feeling from as an aggregate from all the other molecules around, right? That's like that's the pie. You got that much force, right? So how do you divide the pie? Well, here it's divided evenly, like 6 slices. Everybody gets a slice. But up here, say, you may only have 3 molecules on either side. Well, you've got to redistribute that total force among those 3 interactions, right? So they increase in size. So, and you feel most of that increase right at the surface. And that is a stronger force at the surface resisting a pull apart, right? So what's the evidence for that? How do we know surface tension? Well, since my background, my bachelor's degree is in biology. So I was interested in, as far as this goes, surface tension for creatures, right? Insects in particular. And one of them that's fascinating is the water glider, right? These little insects are on top of the water, and they have their 6 feet stretched out, and they're riding on top of the water, and they can move along on top of the water, suspended on their 6 feet. What's holding them up? Well, they're not in the water, so you can't blame that on Archimedes, right? There's no buoyancy there. But you can see at each one of their little pads a depression, right? So they're pushing on the surface of the water, and what's holding them up is the push back from the water, the surface tension. Okay, so I took a long time to explain that, simply because it's a new concept. But if the liquid has very large intermolecular forces, you will see very high surface tensions. Oh, a good example of high surface tension is mercury, right? You can take a dime on a pool of mercury and just drop it there, and it will depress the surface, but it will sit right there. Now, that may not be a good example. If the dime is more dense than mercury, yeah, that's a good example. Oh, how about, have you ever tried this? Take a needle and gently lay it on the surface of calm water. If you're lucky, it'll sit right there on the surface. Okay? That's surface tension. And you know the needle is denser than water. Okay, capillary action, right? What is capillary action? Well, a capillary is a very narrow tube, right? We make them for use in the laboratory, but nature makes them also. Nature puts them in trees and in vascular plants. They use capillaries. Capillary action is the spontaneous rise of a liquid into a tube of sufficiently small diameter. So if you have your tube here, and I'm going to expand the size, it's supposed to be a narrow tube. There's your liquid. It will rise above the surface. What's causing that? Well, there's a play, a balance of forces. Depending on the nature of the liquid and the nature of the tube, you have two types of forces. One is cohesive forces. That is, what are the forces pulling the molecules together? And there are adhesive forces. What are the forces that are pulling the molecules to the surface of the tube? Right? So, if the forces that are pulling the molecules to the tube are stronger than the forces that are pulling molecules to each other, then you will see it rise because they tend to attract to the surface. And as they do, if we could slow it down, use a very high-speed camera, you would see in the beginning it would go to here, and it would rise up here on the sides, and then it would pull. Surface tension would cause that dip to pull up, and it would just keep doing that until when? Until gravity takes over, until the forces of gravity are such that they counteract the aggregate forces developed between cohesive and adhesive. Okay, so that's why the narrower the tube, the higher the rise, right? Because what is operating with gravity is mass. So the narrow tube means less mass, or the same amount of mass distributed over a longer height gives you the same mass for this tube as for a narrow tube with a higher column. That's capillary action. We're still talking about intermolecular forces. Okay, now when we look at a liquid in a glass tube, right? Say when we did experiments with used a pipette, volumetric pipette, or let's see, first semester we did use a burette, didn't we? Everybody know what a burette is? Yeah, we did titrations with a burette. Remember that when you were measuring, when you were marking your place of the liquid in the burette, you looked at the bottom of the meniscus, right? Because the tube is made out of glass, and all of our solutions are aqueous, so it's basically water interacting with glass. The strength of the attraction of water to glass, the adhesive forces, are reasonably strong, but they're only strong at the edge where they contact the glass. So the force of gravity in the center is going to drag the tube, drag the surface down. That's why with water and glass you get a negative meniscus. If we put mercury in there, the cohesive forces of mercury are much higher than the adhesive forces of mercury with glass. So with mercury, right, you would see just the opposite, right? Because mercury doesn't care about glass. It doesn't like glass. There's no attraction between mercury and glass. So you see just the opposite. There we have intermolecular forces balancing one another, cohesive against adhesive. Let's see. That just explains what I told you. Which one dominates? Well, along the edge of the glass, the cohesive forces are dominant. In the middle of the pool of water, the cohesive forces dominate. Now, another measurable characteristic of liquids is viscosity. Right? So if you have, what do they say? It's that guy is slower than molasses in winter. Right? In winter, molasses will be cold, right? So the intermolecular forces holding molasses together would be more significant at a colder temperature. So that slows it down when it tries to move. That's a measure of viscosity. It's a resistance to flow. So if you heat it up, then it flows better. I've also got a degree in food science. And one of the ways we studied transporting materials from one place to another, get them to the factory so they can make your foods, formulate your foods. And many processed foods require sugar, sucrose. Well, the simplest way, the most cost-effective way to get it someplace, and the easiest way to handle it is in a liquid form, because then you can pump it, or you can drain it out of a tanker. Well, fortunately, sucrose is so soluble in water, you can get extremely high percentages of sucrose with just a little bit of water. But as you increase the concentration of sucrose in water, you increase the viscosity. So one way to make it flow better is to just keep your tanker heated or insulated tanker, so that when the tanker is filled with warm sugar water, then when you get to your location, it's still warm and it flows easier. And that's just taking advantage of viscosity of warm liquids versus cold liquids. Also, molecules that are extremely complex, large polymers, tend to have much lower, higher viscosity, excuse me. They tend to flow less easily. And there are a couple of reasons. One is the London dispersion forces are more significant. And there's also entanglement. With large, long molecules, they tend to wrap around one another, right? So that increases their viscosity. Okay, we have two types of solids. Generally speaking, amorphous solids have a disorderly structure, but they're still solids. In other words, they hold their shape and their volume. One amorphous solid that goes unnoticed by the general public is glass. Glass does not have a regular crystalline structure, normally. Now you can create it in such a way that it does have a regular crystalline structure, and there are industrial requirements that are met by that type of form of silicon dioxide. But in general, glass, the type of glass that we have in our windows and our cars, in our mirrors is an amorphous solid. It has no regular structure. In fact, there's one school of thought that says that glass is better described as a supercooled liquid. That makes sense to engineers, I guess, but we'll pass on that for now. The other type of solid is crystalline solid. These have regular ordered structure. And as a consequence, they tend to repeat themselves in unit cells. So you can think of it as stacking blocks, right? As a kid, I used to go to my grandpa's house, and they would always have these little wooden things that you could play and build with. There'd be wooden blocks, and then they had Tinker Toys. You probably don't know what Tinker Toys are. They were precursors to Legos. And the unit cell then could be built up in 3 dimensions, and you can describe the entire crystalline solid based on that one unit cell, because that's the repeating unit in the crystalline solid. So as you might have surmised already, we're going to delve into unit cells in a moment. Okay. But actually, the unit cell is one way of describing a solid. There's a closely related and often interchangeable way of describing a solid, a crystalline solid, with another model called the closest packing model. And it describes the physical arrangement of atoms, ions, or molecules, for that matter, any of those, that minimizes open space, right? So the best way to think of closest packing is, how do gumballs pack themselves in the container, right? If you check them a little bit, then you'll see that they tend to just stay where they are. That's the minimum energy situation for packing solids, to minimize the amount of free space. So, and this closest packing and unit cell are 2 ways of describing the same solid. Remember, when we talk about the physical world is, and when we go to chemistry or physics, we're trying to explain it in terms that we can comprehend. It doesn't change the physical world at all. It just changes the way we think of it. So this unit cell and closest packing, these models, are a way that we use to describe the real system. So in many ways, you could describe it in terms of unit cell, you could describe it in terms of close packing, and they interact with one another in terms of how they describe the system. I think, okay, 2 sides of the same coin. That's one way of thinking of it. Okay, so there are lots of different unit cells, but we're going to focus on just a few, because we don't have the time or the expertise or the need to look at it in more detail than is presented here. And these are 3 different ways here of looking at a cubic type of unit cell. Right? You can have the simple cube, in which case, and let's make this even simpler. Let's focus on atoms, say metal atoms. All right, we can expand it to molecules, but for now, let's just say metal atoms, and that makes it easier to describe. The simple cubic unit cell has 1 atom at the corner of each of the corners of the cube, right? So that's 8 corners on a cube, right? Okay. If we expand that cube into a lattice, then you see this is what it looks like, right? You still have those at each of the corners of the cubes. But in reality, those corners of the cubes are occupied in such a way that each one of the atoms touches the one next to it on the face, right? They don't necessarily cross over that middle space, but on the edges, they do touch one another. And that's an important distinction. It's an important way of looking at it because of the calculations that we want to do with that information. So the space-filling unit cell is many times more useful. Now, what's another possibility? Well, let's say we put a whole atom right in the center. We still have the simple cube, but now we have the body-centered cube with a whole atom right in the center. And then those atoms distributed at the corners. The next possibility, the next most common possibility, is face-centered cubic, in which you don't have one in the center, but you do have one on the face of the cube. Right? So that's 1, 2, 3, 4, 5, 6. You have 6 faces and 8 corners on a cube. So you'll have 6 atoms in this case, one on the face of each cube. And this is what they would look like down here in space filling mode. Right? Notice that with the body-centered cube, the atom in the center touches all the others in the unit cell, but it pushes them away from each other. Right? So they don't touch like they did in the simple cube. In the face-centered cube, you get the face-centered atom touching all the ones around its face, and also touching the other face cubes. One second. Sorry for the interruption. Cats that like to sharpen their claws in my woodwork. Okay, so those are the simplest unit cells, and we'll focus just on those. All right, how do we know the spacing? Let me back up. Let's see. I don't have my pointer, so I'm not backing up like that. I probably should get it out, and I wouldn't have to use my clicker. How do we know the spacing of atoms in a lattice? Well, one way is to use X-rays. And we fire X-rays at this crystal, and we watch both the angle that it bounces and any changes in the frequency. Usually there are no changes in frequency. You either get detection or not detection at given angles. Right? So let me describe what that is. Does everybody understand the concept of diffraction? Okay, so when a light beam, in its simplest description, when a light beam encounters an obstruction, it can do any number of things, but one thing that it can do is, if it encounters an obstruction that is very small, this obstruction serves as a point source for the light to propagate again. Right? So if we have a wave that encounters that slit, then it starts anew from that slit, just like that. Right? That's diffraction. Now, if we have another slit over here, and we get it to start with the same light, notice that you get these, and these lines are the crests, and the white area are the troughs of the wave. Right? So wherever the crests match, or wherever the troughs match perfectly, you get a reinforcement. It's called constructive interference. So at some point down here, where these two waves meet our detector down here will usually show an increased brightness right in the center between the two. And then outside, there'll be a decrease to disappear. And then you'll have lesser intensity at regular intervals. And they'll get less and less intense as you move away. Okay, this is a characteristic of constructive and destructive interference. All right. So Bragg and his associates took that concept and used it to investigate regular crystalline structure solids. And what they would do was, since they knew that the spacing between molecules is very small, they needed to use a light beam of very small wavelength. Otherwise, it would pass right through and not interact at all. Right? So, what they came up with was this equation, and the wavelength here is the wavelength of the X-ray that's used. The D is the distance between the atoms in layers. So we can look at the packing. This is where closest packing model comes in. We can look at the packing of the atoms or molecules in the crystal structure as regularly spaced in layers. So that's the distance between the layers. And then the theta is the angle of incidence of the light beam. Right? So that's the mathematical. Here's what it looks like in a picture. Right? So you get one layer here in your closest packing, and you get another layer here. And what happens is when the X-ray encounters an atom, it reflects like that. So what happens also is at the next layer, you get another reflection. And if you look at them at the proper angle, you will see these crests matching, and your detector over here will pick up an increase in intensity. And that only happens at a given angle. Well, it happens at several angles, right? They're called orders. But the first order, we'll stick with the first order, and that's what N stands for, right? The first order angle is N equals 1. And what you end up with is your sample is sitting here, and X-rays are coming in here, and they're bouncing off at a given angle. So that angle theta, I think, yes, that's right. Your detector is over here. Right? It won't actually be an eyeball, right? Because you want to fry your retina. But your detector is moved at an angle, and when it encounters a maximum intensity, you can measure that angle. And using the Bragg formula, you can back calculate for your unknown distance and find out what is the separation of those molecular layers. Okay? That's all there is to it. I used to use this when we were investigating for my PhD. I was in soil science. So we would investigate the nature of the clays that we isolate from different soils. And we could tell what type of clay it was by this measurement. So the clay would be sitting here, and clays are usually in plates, right? So you put them in a slurry, and then you dry them down, and they settle down in plates, in layers, and you can measure the distance between the layers in the crystal structure of your clay. The instrument I used was old, I mean, it's ancient, but it still worked. Okay. So what do we do with that? Well, that's one example of measuring the layers in a crystal structure in 2 dimensions. But we're interested in the 3-dimensional character of a crystal structure. And to do that, we're going to get a a pattern here. Let's see, where's my pointer? There it is, right there. We get a pattern that can be interpreted in this two-dimensional image as derived from 3 dimensions. It's very complicated, and when the technique was first invented, when it was first used, it sometimes took years to tease out information from that pattern. In fact, that's what happened with DNA. It took them quite a while to deduce that that pattern was due to a double helix. Now with the computing power of our modern computers, that can be done in seconds. And of course, they have libraries of these things stored in the computer that the patterns can be compared to, and shorten the workload considerably. Okay, so that's what X-ray diffraction and the Barrett equation are used for, to deduce the structure of your crystal lattice. Okay, types of crystalline solids. You can have arrangements of ions, right? So we could have sodium and chlorine, right, arranged in regular structure for table salt. That would be an ionic solid, right? And what's the structure of, what's the unit cell of this? Well, we don't know exactly from looking at it, but if you take a microscope and look at salt spilled on the countertop, you can see they're all cubes, right? So there's some type of cubic structure that's responsible for that lattice of our ionic solid, sodium chloride. Molecular solids can also be bound together in a crystal lattice structure, but they usually take much lower temperatures to acquire, because the bonds that hold them together are much weaker than ionic, right? They're dipole moments, maybe, or even London dispersion forces. In those cases, be careful with those solids, because too much energy from your probing light source, and you're going to destroy the structure. So it takes a lot of care. And then there are atomic solids, like the metal structures that we discussed earlier. Those are the 3 types: ionic, molecular, atomic solids in crystal lattice. All right, 3 examples. We covered sodium chloride already, right there. Right? Here's a molecular structure. That seems to be very interesting. In fact, that's diamond. Diamond is a molecular crystalline structure where every carbon atom is surrounded by 4 others. So it's a tetrahedral arrangement. And in a diamond that has no flaws, the entire diamond is one crystal molecule. In other words, if you were small enough, you could hop from one carbon atom across the bonds from one side to the other and never have a break. Other possibilities are molecular structure, like this. This would be an example of an atomic structure for diamond. A molecular structure would be frozen water, right? In snow, gives you that regular structure. So those 3 examples. And there are different types of forces holding them together. For the regular atomic solid, in this case, those are covalent bonds. Now, atomic solids, crystalline solids, are not always held together by covalent bonds, right? Metallic structures require a different type of bond. The ionic solids, there's only one type that holds them together, and that's ionic, of course. And the molecular structures, they are usually held together with either dipole moments or, for some, the London dispersion forces. Now, for this example, covalent is right, but it's not always covalent for atomic solids. There's another class, a metallic bond, that we're not even talking about here. Okay, and this is just right out of your book and gives you one table with all that information together. Anybody need to take a break? I need to take a bathroom break. So what I'm going to do is pause, not pause share. Stop share. I need to pause the video. I guess I'm going to have to stop the share, pause the share. Your screen sharing is paused. That's not going to help. Pause the record and bring up the share again. There. Let's see. I guess I'm going to have to find out where I left off. Oh, good. There we go. Okay. All right, so now we're going to take a look at how atoms arrange themselves, particularly in this case for metal atoms, in a closest packing environment. Now, I've got a video in here. It's kind of long, and the guy's got an accent. He's from India, so sort of adjust your hearing ahead of time so you can pick up the. He does a very good job of explaining how this closest packing model is built up. He starts with one dimension and builds it up, and I think it's very good if you can get past the accent. First, there are certain assumptions that we have to make for the closest packing model. One is that all the atoms are uniform, the same size, and we treat them as hard spheres. Right? So I know that's a stretch. We know that atoms are not hard spheres. But for our purposes, we do that to simplify the model. And these spheres are packed in layers. Right? So you can view them once we get past the one-dimensional into the two-dimensional and then start stacking them in 3 dimensions, then they occupy layers. Okay, so let's see. Here we go. I may have to start it. No? Don't do this to me. Here we go.
Constituent particles in a crystal may be thought of as solid spheres, and in this video we shall try to understand the close packing of spheres in a 3D space, leaving minimum vacant space. Packing in one dimension. There is only one possible linear one-dimensional arrangement possible with spheres. They queue up linearly, each sphere touching the adjacent spheres like this. Packing in 2 dimensions. To arrange spheres in 2 dimensions, we take the linear one-dimension arrangement that was shown previously. There are 2 ways by which we may arrange the spheres in a 2-dimensional platform. They may be arranged like this. Note that each linear arrangement are aligned vertically. Here, the vacant space is this. Now, in this packing, the spheres take up only 52.48% of the available space. Here, a single sphere touches 4 other spheres. If we join the centers of the spheres, we get a square. Therefore, this packing is called square close packing. A second way of arranging the linear one-dimensional arrangements is to keep the spheres of the second linear one-dimensional arrangement in the depressions of the first, like this. Here, every alternate linear arrangement has the same alignment. These are the vacant spaces, which is visibly less than the square close packing and hence more efficiently packed. In this packing, the spheres occupy 60.4% of the available space. The voids created in this packing touches three spheres forming an equilateral triangle and are called triangular voids. A single sphere touches 6 other spheres, and by joining the centers of these spheres, we get a hexagon. Therefore, this packing is called hexagonal close pack. Packing in 3 dimensions. Taking square close pack 2-dimensional layers. This is done by placing a 2-dimensional layer just above the first layer and so on. All the layers are vertically aligned. Taking hexagonal close pack.
Just a comment here. Notice that when you pack them that way, you get a simple cubic unit cell.
Packing 2-dimensional layer. The first layer contained red colored spheres indicating the alignment of the layer. This alignment is called A. These are the void spaces of the layer. We have to place a layer on top of this layer. For efficient packing, we will have to place the second layer in such a way that the spheres are exactly over the triangular voids of the first layer. Only these triangular voids can be covered. The spheres of the second layer are blue in color, which indicate that this layer has different alignment, and this alignment is called B. We can no longer see all the void spaces created between the 2 layers. In order to overcome this problem, we will make the second layer transparent. Now we can clearly see the 2 different types of voids created by these 2 layers. These are called tetrahedral voids, marked by the letter T. And these are called octahedral voids, marked by the letter O. The tetrahedral voids are created by 4 spheres. First, we make the spheres a little smaller in order to understand the shape. Then we join the center of the spheres by straight lines. The shape is a regular tetrahedron. So the void is called tetrahedral void. The octahedral voids are created by 6 spheres. Here also we make the spheres a little smaller, then join the center of the spheres to get the shape. The shape is a regular octahedron. Placing the third layer. This can be done in 2 ways. These are the triangular voids of the second layer that are not involved in making octahedral voids with the first layer. By placing the third layer above these voids is one way of placing the third layer. If we do this, we can see that the first and the third layer have the same alignment A. With similar reasoning, we keep a 4th layer on top of the third layer and see that the second and 4th layer have the same alignment B. This pattern of close packing is called ABAB type pattern. We make spheres a little smaller and join the centers with straight lines to understand the shape. It is my belief that this is the unit cell of this close packing because it is the smallest unit that may be repeated to form the entire crystal. The top of this unit cell has the shape of a rhombus having gamma equal to 120 degrees. 3 such rhombus form a hexagon. For a better visual cognizance, this shape is taken as the unit cell of this close packing, which is called hexagonal close pack or simply HCP structure. Another way of placing the third layer is to cover the octahedral voids of the second layer by placing the spheres of the third layer above the octahedral voids made by the first 2 layers. The alignment of the third layer is different from the first two layers, and so the color of the spheres have a different color, that is green color. Let this alignment be called C. Using the same reason, we can cover the octahedral voids created by the second and third layers by a fourth layer. It will be found that the fourth layer has the same alignment as the first layer. So this pattern is called ABCA type pattern. Now again, making the spheres little smaller and joining their centers by straight lines, we get the shape of this packing like this. The unit cell of such a packing is this. This is nothing but a face-centered cubic lattice. So this type of packing is called cubic close pack, or simply CCP, or even FCC structure.
Okay. Yep, let the credits roll. One of the good things about that presentation was not that it keeps repeating itself. There. Was that the narrator drew a relationship between the type of close packing arrangement and reference to the unit cells. So the two types of close packing that were described were AB-AB packing, in which the third layer is laying directly over positions of the second layer below them, thus AB, AB. And then the ABCA layer, which is in the next slide, I think. The third layer bears no resemblance to its position in relative position in space to the two layers below it. So you have ABC, and then you start getting the repeating again with the fourth layer. All right, so with the ABAB, you also get a unit cell that's hexagonal in shape. Now that's one that we didn't describe. We only described earlier the cubic cells. So this hexagonal closest packing is related to the hexagonal unit cell. So anytime you have an ABAB, you also have a hexagonal unit cell. Anytime you have an ABCA, we're talking about a face-centered cube. Okay. Now those are not the only way to stack, but like I said earlier, we're limited on time and need, so we're focusing on just some of the simpler versions. This cubic closest packing is also face-centered cubic for the ABCA.
May I ask a quick question?
Sure.
I didn't mean to interrupt you, I'm sorry. So just for my understanding, they will always be different layers, but the layers will always align, correct? Like there will be different closet packing layers, but those layers will always align within each other, right? To make that arrangement.
Okay. Yeah, for simplicity's sake, these might be different colored spheres, but they're actually all the same atoms.
Okay. Okay.
So they're only different colors so that we can see the difference in the way they're oriented in space.
Okay. I'm sorry. I knew that might have been a dumb question. I just needed to hear it.
Oh, no. Ask anybody else that's had my classes before. I love dumb questions. In general, what's trying to happen with, actually, this is a general concept in chemistry. Anytime you have a physical or a chemical process, and chemistry tends to co-opt both, the tendency is toward minimum energy, right? So the minimum energy situation is whatever can be obtained in the near term by the system. So if it has an AB arrangement, that for those atoms is their minimum energy situation. And by that, I also mean they leave the least amount of unused space behind. For other types of atoms, and most of these are metals, because most of the periodic table is metals, the ABCA type packing generates minimum energy for those elements. And the only difference, since these are all the same elements, the only difference is what is their orientation in space. And you'll notice that this A layer lines up with that A layer, but it doesn't line up vertically with the B or the C layer. That's why it's ABC, and then we start repeating with the A again. Okay. So the hexagonal closest packing model, which was what, ABA, the hexagonal closest, the author or the narrator preferred to stop at that point and just say the unit cell was hexagonal closest packing. But if you carry it a little further, you find that the unit cell for the hexagonal closest packing can be described as a unit cell of face-centered cubic. Right? So hexagonal closest packing is also a unit cell of face-centered cube. Now, if we go to the ABCA, we find that this unit cell is also face-centered cube. Okay, that's interesting. Caught me off guard. I thought I was going to be profound, but well, it's simple. In this case, the cubic closest packing, ABCA, also gives you a face-centered cubic cell. Now, that's not to say that everyone is like that. Let's just, for the time being, assume that for our purposes, we're going to focus on the face-centered cube. So what we need to know, we need to deduce from this face-centered cube is how many atoms does that actually represent in that unit cell, right? Because you've got the face-centered atoms have been chopped in half, and the corner atoms have been chopped in eighths, right? That's an eighth of a piece of an atom. So we need to add up all those pieces to find out what does this unit cell actually represent in terms of whole atoms. So that's what I'm going to do next. Okay. I'm not going to do that next. The coordination number, a definition of a coordination number is just how many atoms is one in the center touching.
Your board is falling behind you.
Sorry?
Your board behind you fell.
Oh, I must have bumped it. I got things packed in here so close. This is a human closest packing unit cell. So I want to get this as close to the camera as possible so you get better resolution. Okay, back to the coordination number. Coordination number can be used in means a little slightly different depending on the area of chemistry that's being investigated. In this case, coordination number is simply the number of atoms that the center atom is touching. And for the ABAB, the hexagonal closest packing, we have 12 atoms that are coordination number. They're touching the center atom, and they represent a octahedron. the hexagonal closest packing refers to this hexagon in the middle, right here. That's just a single layer. But the three-dimensional arrangement is octahedral. Okay, so now we can talk about the net number of spheres in this case, in a face-centered cube. We can also take any one of the other cubic unit cells and deduce how many whole atoms it represents. But we're going to start with the face-centered cube. Here we go. There's our face-centered cube in the space-filling model. What we need to do is say how many does each one of these represent. So there's a half an atom, and how many of them do we have? We got 1, 2, there's one over here, 3, 4, and then we have one on the bottom, 5, 6. So we have 6 faces on our cube holding a half an atom. So a half of a 6 is 3, right? So the faces represent 3 whole atoms. The corners represent 1/8 of an atom, and we have 8 of those, right? So that represents only 1 atom. Add them together, and a face-centered cubic unit cell represents 4 atoms. Okay? Simple cubic, we could look at it the same way, right? So simple cubic, we only have atoms at the corners. So that's 8 of them. 1/8 times 8 is 1 is the simple cubic. Right? So the simple cubic is represented 1 atom. The face-centered cubic, we did that one already. That's 4, excuse me. 4. The one we haven't done yet is the body-centered. Right? So where's the body-centered? Oh, we didn't do the body-centered. All right. So let's do that one on the board. Where's my, here it is. The body-centered cubic right. So there's our cube. The body-centered is going to have 1 in the middle. Cubic. And then it's going to have 1 at each corner. And none on the faces, right? So there's 1 atom in our unit cell, and there's 8 times an 8 is 1. So the body-centered cubic unit cell is equal to 2 atoms. Okay? So simple cubic is 1, body-centered is 2, and face-centered is 4. Okay, now to, let's see. We want to use this information to tease out useful relationships. Actually, not useful, useful measures of solids. And one of those is what's the density of the solid? Or flip side of that coin is maybe we want to determine what's the molar mass of the substance. So what we need to know is something about the cube, the edge length of the cube, in relation to the atomic radius of each of the atoms in the structure, right? And the derivation of these formulas just takes too much time for this. I've got some some documents that are in Blackboard. If you want to go look at them and see how the geometry works to derive these formulas. But for the simple cubic, the length on the edge is just 2 times the radius, right? Because you have a cube. Oh, before I run out of time, just a word. Anybody who's had my course before knows that if we run out of time, you're obligated till 11:15. If you have to go, fine. I'll just keep talking and finish the video. Right? And then it'll post later. But if you can stick around, that's okay too. I'll keep going until this topic is done. Okay, so the edge length.
I have to go, Dr. Bly, but I'll watch the end of this once it uploads.
Okay, that's fine.
I just wanted to let you know, but I do have to go.
Okay, we'll it'll be posted within 24 hours, and then next Tuesday we'll do chapter 11. And by next Tuesday, I should have the video for the lab done also. Okay, so that you can take that information and generate your first report. Okay?
All right, thank you.
All right, so bye. So there's our cube again. And now drawn that way, it's not obvious that the edge length is 2 times the radius, because the radius is right here. That's R. But in the simple cubic, these spheres touch one another. So 2 times the radius is the edge length. That's the easiest one right there. Okay, for the face-centered cubic, the one that gives us 4 atoms per unit cell, the edge length is the radius of the atom times the square root of 8. Right? Like I said, we don't have time to derive that, but take my word for it. And by the way, in the review documents that are in Blackboard and in the useful information that will be on Blackboard in the same folder as the exam, you will have those formulas given to you right there. So just you can go in without taking the exam and look at those things and find out where they are, so that when you decide to take the exam, it won't be a big shock. You'll see all these formulas and numbers up there on your screen and just hitting you from all sides. You can orient yourself ahead of time. And these formulas will be there in that document. Okay, what's the other one? Body-centered cube. Okay, for the body-centered cube, the edge length of our cube is the radius of the atom times the quotient of 4 divided by the square root of 3. Okay, so this required some geometry and trigonometry, and you can either take my word for it or go look up those documents, and they'll give you a detailed description of how those values were derived. Okay, so we can use this information. All we need to know is what is the unit cell for a given element, right? For this example, the silver is arranged in cubic closest packing as a face-centered cubic, right? And the unit cell edge length is 409 picometers. Right? So what we want to find out is the density of silver, right? So what do we need to know for density, right? I always go back to basics. If you want to know the density of something, you need mass and volume, right? So what's the volume of our unit cell? All we need to know is the edge length and cube it, right? But we need the right units. A picometer, normally the units for this are cubic centimeters. So you need to change your picometer to centimeters. Then when you cube it, you'll get cubic centimeters. So that one is easy to fill in. You're given that information right there in the problem. The other part, the mass, you have to determine how much mass is in that unit cell. So we know that the face-centered cube has 4 atoms per unit cell, occupying that volume that we can calculate. So we need to find out, convert those 4 atoms into a mass. Right? So that's what the calculation is going to do down here. Right? So we have 4 silver atoms in a unit cell. We have the volume of the unit cell is that edge length cubed, but of course we have to change that to centimeters. So when we do change it centimeters and cube it, we get this volume for the unit cell. Now we need to, what's the mass? Well, if we've got 4 atoms, how much does 4 atoms weigh in terms of grams, right? So 4 atoms, and it's 107.9 grams per mole, but how many moles is 4 atoms, right? So we have to plug that in here also, change atoms to moles, right, with that relationship. And then here's our divider right there, and we plug in the volume. And when you do the crunch the numbers, that's the thinking part. Then when you crunch the numbers, you get 10.5 grams per cubic centimeter. That's a calculated density for silver. If you actually measure the density of silver, it's extremely close to 10.5 grams per cubic centimeter. And that's just confirmation that our method works. Okay? Now, I'm pretty sure that in the review document, there's at least one more calculation of that kind to give you practice.
It's also in the homework.
I'm sorry?
A lot of it. It's
Oh,
also in the homework, a lot of it, so I'm pretty sure. Yeah.
Oh, okay. Okay.
The end of the chapter.
Okay. End of chapter homework. Good. Good. Okay. So earlier we talked about what types of bonds are involved in the construction of crystalline solids, right? And the one that we didn't talk about was, what if those atoms in that crystalline solid are metals? What holds them together? It's not a covalent bond, and it's not ionic bond, because these are uncharged, right? And it's not van der Waals forces, because the bond is much too strong. So we need another model for how metals are bound together. The earliest model was called the Electron C Model. And what that basically said was, you've got metal atoms floating in a sea of metal cations floating in a sea of electrons. And that was okay in the beginning, but that really didn't give you any predictive power. So, molecular orbital model became very handy, right? And we've talked about that in the first semester, haven't we? Molecular orbital. Yeah, I'm pretty sure we have. Okay, so that's the band model. So what does that mean? Well, there's the C model, and nowadays it's pretty useless. It's just historical significance. The molecular orbital assumes that the entire amount of metals, right, just like any molecular orbital model, all of the orbitals that are available for bonding from each of those individual atoms is blended together into a group of molecular orbitals. And then you fill the electrons into them. So if you have lots of metals and lots of orbitals to play with, the molecular orbitals are virtually infinite. And the energy difference between each one is so close that just a whisper will move an electron from one to the next. That's why metals are such good conductors of electricity. Just a little bit of push and the electron goes whoosh to the next atom, right? So in graphic form, it looks like this. right? The molecular orbitals for two metal atoms are fairly well separated in energy. But the more you get, the closer they get together. And when you get to a mole of them, it's virtually a continuum. So that does explain why metals are good conductors of electricity, good conductors of heat, and also their bonding is particularly strong. Otherwise, we wouldn't have things like steel or titanium structures for the SR-71 Blackbird, things like that. Okay, this is another way of looking at it. You have the filled molecular orbital. They call it the highest occupied molecular orbital is this one, the HOMO. And then the lowest unoccupied molecular orbital is the LUMO. That's the one that's in, let's see, where's my pointer? Here it is in this color. So they're very close together, and it's easy to move electrons from one to the other. And all you have to do to get access to another atom is just to move into the molecular orbital and find yourself over there next to that one. And if there's a push from one side, it's like a river. It will not be denied. Okay. So now we come to the concept of alloys, right? Up to this point, we've been talking about solids that are constructed of metals, pure metals, right? But in very few instances, pure metals or pure elements are not very useful. I mean, their final use is based upon doping them with various other elements to tailor the way they respond to a stimulus. One type of alloy is the substitutional alloy. That's a case where, say you have copper as your pure, and you have pure copper metal. So each one of these is copper atom. And a substitutional alloy will take one of those out, put something else in its place. Right? So if we do that and we put nickel here, or maybe nickel over here, and maybe copper here, copper here, copper here, rest of them copper, you have a substitutional alloy that's commonly called brass. So that's one type. I'll leave that up there. The other type of alloy is one which, remember those voids in our packed model? Spaces in there. Well, if you get an atom that's small enough, you can stick it in those holes. That's the interstitial alloy. And the best example of that kind is iron. All of these are iron. And right in here is carbon. When you do that to the tune of, say, 0.5% or even less, you get steel. Actually, 0.5% is too high for steel. 0.1% to up to maybe 0.3%. Would be an interstitial alloy of carbon in iron that makes steel. All right. This type of alloy modifies the behavior of the copper in such a way that, well, I don't know, it gives you resistance to corrosion, for instance. But this one, what happens if you've never held a piece of pure iron in your hand, you can take your fingernail and scratch it. It's very soft. But if you stick some carbon in there, what that does is it tends to lock that crystalline structure in place, keeps it from shifting, and that adds to hardness. If you go to very high amounts, you get things like wrought iron, right? Very high amounts, or let's see, I'm trying to think, cast iron, right? Your cast iron cooking utensils are made of very high percentage carbon, like 4 or 5%. And they're very resistant, they're very hard, and they resist wear very easily, but they're very brittle, right? Because at a certain point, sticking that many carbons in there destabilizes the bonds between the iron atoms, right? So then they become brittle. The happy medium for construction purposes is put just a little bit of carbon in there, try to lock those layers in place, and you get steel. Okay. I could go into the history of, I'm already past time, so let's move on and see if we can finish this up. So there are your examples: interstitial alloy, brass versus steel. By the way, brass is also a solution, a solid solution of copper and zinc. Just to go back to our first semester beginnings, it's a homogeneous mixture. It doesn't look homogeneous there, but believe me, it is.
In this animation, we will be visualizing the diamond form of carbon. Carbon forms 4 single bonds using sp3 hybridization. Each carbon atom is bonded to 4 nearest neighbors, forming a 3-dimensional lattice. These covalent bonds make carbon in the diamond form a network solid. Network solids are very hard and have high melting points.
Okay. Next, well, there's diamond. All right, here we're drawing a distinction between the different solid forms of carbon. This network solid of carbon as a diamond is locked in place with all covalent bonds, whereas graphite has covalent bonds in layers, right? Hexagonal layers here, but the bonds that hold them together, one to the other, would have to be van der Waals. Which is also true, but London dispersion forces. They're kissing cousins. The layers of graphite slide past one another. It doesn't take much effort to make them. That's why graphite is used as a dry lubricant. I used to squirt it down my motorcycle cable guides to lubricate the cables. Why? Because it's not wet and it won't attract dust, but it still allows the cable to slide with very little friction past the inner walls of the cable and prolong the life of your cable and make it easier to work. Okay, so for a typical metal, the difference in energy levels between those that occupy electrons and those where you could push electrons to get them to move from one side to the other, a typical metal, those energy levels are very close together. Right? That's why they're good conductors of electricity and heat. But for diamond, the difference in energy level between the filled molecular orbitals and the empty ones is a huge gap, which makes diamond a very good heat and electrical insulator. In fact, if you go to a jeweler and you want to say insure your diamond, first thing they're going to do is prove that it's a diamond. So they have this device that they put right up against the diamond, and it measures the heat conductivity of the diamond. If it conducts heat too fast, it's not a diamond. And they have numbers that go with that. Because diamond is not supposed to be a good conductor of heat. It's supposed to be a very good insulator. Simply because the energy levels between these two layers, here and here, are so wide. Okay. So other types of arrangements can occur. The bonds that hold the layers of graphite together are very strong. In fact, they're much stronger than you would expect between one carbon and another carbon. And what we get is these orbitals here that would initially be unused between the two carbon atoms, overlapping. And in fact, they smear one another around that donut above and below. And what that does is it tends to strengthen the overall structure. That's called a pi bonding system. We're not going to spend a lot of time on that. It's just interesting to know. And if you head for organic chemistry, you'll get more of it anyway. Right? So if you don't want to ever hear of it again, don't take organic. Okay, here's another type of network solid, the ceramic. Ceramic is actually an operationally defined solid, which means that it could be almost anything. It's just characterized by basically non-metallic materials predominantly. And for example, a good ceramic would be, well, your coffee cup is made out of a certain type of clay that's been fired to make it react chemically with its neighbors and form this crystal structure. Right? They're very strong, but they're brittle. But they also have extremely good abrasion resistance and resistance to high temperatures and chemical attack, right? So that's why the automotive industry is interested in using ceramics in their engines, either to build the entire cylinder and piston out of ceramic because it wears so well, or to coat the surfaces with a ceramic. I don't think there are any commercially available yet, but their high resistance to heat is also valuable. You can get ceramic coated metals at any department store or on the internet in the form of cookware. Right? You get the ceramic coated cookware, and it's like Teflon used to be. Your food just slides around on it, and it's very resistant to scratching, which Teflon is not. And very often they'll be kind of slightly reddish in color, right? So I often wondered about that. Why are they reddish in color? Well, ceramics are good resistance to wear, very strong, but they're brittle, so they have that metal backing in your cookware to hold, keep them from breaking up. They're resistant to heat and attack by chemicals, which is not too bad, but let's focus on the resistance to heat. If they're resistant to heat, that means they don't conduct heat very well. And that's not good for cooking food, right? You need something that'll conduct heat. That's why cast iron cookware is so good, because it conducts heat very well. So what do? Well, they infuse the ceramic with copper and gives it that red color. Copper will conduct heat, but if they don't put too much of it in there, then they still retain the desirable characteristics of the ceramic. Okay, semiconductors. All right, what's a semiconductor? Well, study of electricity involves conductors versus insulators. right? So that you just have those two. You have the copper wire surrounded by the insulator so you don't get shocked or you don't short it out somewhere, and you wire things together. But there are many advantages to using that space in between the conductor and the insulator. You've probably heard me say many times that when I say this versus this, there's usually a continuum in between. And when we say it's either that or that, simply to help us comprehend. But in nature, there's always a continuum. Well, we've taken advantage of the continuum in the middle here. These are semiconductors. They only conduct slightly. And with that characteristic, we've learned to control how they conduct and when they conduct. Right? So when we do that, we can create microscopic, they call them logic gates, that can be turned on and off to conduct. Right? So theoretically, off would be a 0 and on would be a 1. So now we're talking about binaries. And you put enough of those in a chip and organize them in such a way that you can control how information goes in and comes out, and you've got the makings of a logic circuit. It's either yes or no, ones or zeros, your binary code. Well, you can make these semiconductors two different ways. We start with a pure material. And one of the reasons that silicon was chosen as the starting material is because it's right here on that, let's see, can you see? On that imaginary line between metals and nonmetals. Silicon is a metalloid. So it will respond to doping from either one side or the other of that line. Right? So silicon is like carbon. It has a complete, well, it actually has 4 valence electrons, which means it has rooms for 4 more. But it could also give up an electron. It could go low or it could go high. So what do? Well, I better keep this out. With silicon, if you dope it with an element from the right-hand side, that means that dopant has extra electrons. Right? So now the overall character becomes an N-type semiconductor. N meaning negative, extra electrons. Right? If you dope it with something from the other side, like gallium, it's deficient compared to silicon by 1 electron, and you get a P-type semiconductor because you've got 1 less electron in that position. Like gallium versus silicon would be absent 1 electron, whereas phosphorus would be an additional electron. Okay, so that's where the P-type or N-type semiconductor comes from, is just the way that you dope the pure substance. Now, silicon's not the only substance that's used. It's the cheapest, right? Silicon's everywhere. I mean, the Earth's crust is predominantly silicon and oxygen. And any beach you walk on is just chock full of silicon dioxide. So the raw material is everywhere. It's just making pure silicon is a technology in itself. But once you get the pure silicon, then you can dope it with the more expensive stuff. If you want a more rugged semiconductor, you want to use something different than silicon. So you go up to maybe germanium would be a good starting material. Or even antimony. Anyway, they're more expensive, but you get the same result. And what you want is a semiconductor that's designed for its purpose. And on the Earth's surface, we're protected from ionizing radiation, right? Which is bad for microcircuits, because any stray particle that comes slamming into your semiconductor could knock an electron off where it shouldn't be and destroy it. So things that we put in space, if we make them out of silicon semiconductors, you either shield them as best you can, or you make them out of more rugged material, right? Which means expense. Okay, so let's see, am I close to the end? This is just an added explanation for doping, right? And what it looks like. We talk about when charges move around in a semiconductor, we say for the N-types, we move the electron. That's easy to comprehend. But for the P-types, we say the hole moves, which in reality is not the case, but conceptually, it's easier to discuss the P-types as moving holes.
Water is a molecule made from non-metal elements. In the solid phase, these covalently bonded molecules are attracted by weaker dispersion forces. Long-range order exists between molecules that pack in regular formation. Molecular solids are relatively soft and have low melting points. Crystallized water occurs in many interesting forms, including snowflakes.
Sodium chloride is typical of ionic solids. The crystal contains alternating sodium cations and chloride anions packed in a three-dimensional array. Ionic solids are brittle if deformed and will fracture along planes of packed ions.
Sorry about that. A word of explanation. I take medicine to control blood pressure. It has two ingredients in it. One is a vasodilator, and the other is a diuretic. So it makes you have to go to the restroom more often than you normally would. Okay, so there's quite a bit more that we need to cover. I'm sorry about that. Like I said, if you need to go, don't feel obligated to stay. The recording will be uploaded shortly. So ionic solids are typically very stable. They're very high melting point, and the electrostatic forces hold them together with tenacity. The oppositely charged ions are strongly held together. Now, you may recall in first semester, the ionic bond itself is weaker than the covalent bond. But when you get them all together in a regular lattice structure, it can take a lot of energy to disrupt that arrangement. So things like sodium chloride will take thousands of degrees of temperature to melt them. And in fact, there's been some engineering uses for sodium chloride, liquid sodium chloride as a coolant in nuclear reactors. Right? So it's not unheard of to use liquid ionic, formally ionic solids. So the different melting points that are attributed to ionic solids are due to what characteristics? Well, basically, the difference in charge is the first consideration, right? If you have, for this illustration, if you have two positive charges here and two negatives, the intrinsic attraction is going to be stronger than it would be for one sodium and one chloride. But also there is the effect of distance, right? Because electrostatic distance is subject to the area law, the square of the distance. So if you move twice the distance away from an object, you feel 1/4 of the force. The same thing with gravity, right? It obeys the square law. So we've got two things working here. If the atoms are huge, like these two, like chlorine is a huge atom, whereas oxygen is a smaller anion, and magnesium is a smaller cation than sodium, then you get both the charge difference and the distance. And you would expect magnesium oxide to have a much higher melting point than sodium chloride. And in fact, it does. Oh, okay. Any questions about that? I'm moving on to another topic. Okay. So our Indian narrator earlier talked about the types of holes that were found in the closest packing model. Right? When you have these laid together in this form, you have a trigonal hole, right? And that's just because you have three atoms touching each other, and this would be on a single layer. You would have that trigonal hole. And for binary ionic crystals, that is, where you have a cation and an anion in the same crystal structure, like sodium chloride, the trigonal hole is usually too small for most cations. So it would not be occupied by the cation. Instead, it would be placed in another layer, right, so that it could get as close as possible to the anion and feel that strength of electrostatic attraction at minimum energy. Okay, so if we have a tetrahedral hole, now we're talking about 3 dimensions. When these spheres sit as, if they're all cations, for instance, then you get a cation sitting in that trigonal gap that we saw before, then you get a tetrahedral hole. You would need a very small anion to fit in there if that were the case. I misspoke. Those blue circles are not zinc. Those blue circles are sulfide. Okay, let me say that again. The tetrahedral hole here is formed by the sulfide anions. Okay, now, and that makes sense, right? Because what happens with an atom? If you add an electron, it gets bigger, right? If you take away an electron, it gets smaller. So the metal is going to be the smaller ion because we have removed electrons from it. So the zinc is the small ion that fits in those holes. The tetrahedral hole for the octahedral hole for hexagonal closest packing. This could, and usually is, occupied by the counter ion. So, rule of thumb, if we have, if we're looking at the hole for placing a counter ion, the smallest one is the trigonal, next biggest is tetrahedral, and the largest hole is the octahedral hole. Right? So the octahedral holes, in my mind, would have more available space for different types of counter ions. And the tetrahedral and trigonal would be more limited. Okay, here's another table straight out of your book, and it just puts everything together in one place. Talks about the types of solids. Atomic solids could be either network, metallic, or group 8A. We didn't talk about that one very much. What's group 8A? The noble gases, right? So when they form solids, the only forces that are involved for these atomic unit in the structure are London dispersion forces. They have very, very low melting points, as opposed to network solids that have directional covalent bonds. They're very hard, and other characteristics. Then you have molecular solids. These were all atomic over here. Moleculars, where you start with a covalently bound group of atoms in a molecule. Then how do they interact? And what intermolecular forces are required to hold them together? That's when we started talking about dipole-dipole interactions, and for nonpolar molecules, the London dispersion forces. And then the last one we just discussed was the ionic solids and the things that hold them together. Okay, so there, I think we're going to focus on liquids and gases now, or behaviors of predominantly liquids. And one measurement that can be made for a liquid is its vapor pressure. How do you measure the vapor pressure? Well, you need a liquid that's placed in an enclosed container and allow the evaporation of the liquid to reach equilibrium with condensation. Right? So in the beginning, initially, it's all evaporation. There are only molecules leaving the surface. But eventually, you get impact of these molecules with the surface, and they return to the liquid state. Now, what determines how much of the liquid will go into the vapor phase is dependent upon the intermolecular forces that hold the liquid together. If the forces are very weak, then there will be a high vapor pressure because the forces that hold them in the liquid are weaker, so they just as soon be in the gaseous phase. And you can measure that. You just need to stick a gauge up here or some other way of measuring the impact of those molecules on a membrane, and you can deduce the pressure. Not deduce, you can measure the pressure. Okay, so this is what it looks like when you first put the liquid in the container. The rate of condensation is 0, and it gradually increases as the rate of evaporation approaches it, and they match. At that point, they're in equilibrium, and that will establish the vapor pressure at a given temperature. Right, vapor pressure is dependent upon temperature. Why? Because the temperature is an indicator of average kinetic molecular energy. And the higher the molecular energy, the more impacts there are, the more energy there is in the system, and that energy can break bonds. So if you change the temperature, you change the vapor pressure. Let's see, we talked about that. What's the vapor pressure of water at 100 degrees centigrade? How about 1 atmosphere? That's the boiling point of water at sea level. 1 atmosphere is the vapor pressure of water at 100 degrees centigrade. Now, if you go to a higher altitude, then 1 atmosphere is different. No, the atmospheric pressure is different. You decrease the pressure, then it takes less energy to vaporize molecules from the surface. So that's why the temperature, the boiling point of water, decreases with altitude. Because if you decrease the external pressure on the surface, then it takes less energy to liberate molecules from the surface of the liquid. That's why it takes longer to boil an egg in Denver than it does here in Beckley or on the coast. Because you can't get the water hot enough. So the egg cooks slower. That's why pressure cookers are very useful at high altitude. Okay, so here's an illustration of vapor pressure. And it uses a mercury barometer for our example. So in the first example, this is where Torricelli built his mercury barometer. And, you know, he filled up this tube, put his thumb over it, submerged it in the mercury, and then let it drop. That was a vacuum. There's nothing up there. Well, technically, there might be a few mercury atoms, but for all intents and purposes, it's a vacuum. Very, very low pressure. But if instead, before you fill the tube with anything, you put something else in it, like water or ethanol or ether, and then cover it with mercury, then submerge it, you'll notice that the level of the mercury is lower than it was before. There's some back pressure in here from the vaporizing liquid. And that difference is the vapor pressure. The difference between this one and that one is the vapor pressure of that liquid. So in this case, water is only 24 torr. It has relatively low vapor pressure. And that's because the intermolecular forces holding water in the liquid state are very high, hydrogen bonds, right? So let's do it with ethanol. We find that ethanol has the capability to hydrogen bond, but the number of hydrogen bonds are decreased from water. Water has 2 hydrogen bonds per molecule. Ethanol only has 1. So the strength of attraction, the bonding in ethanol is much less, so its vapor pressure is higher. And then when we get to ether, the only possibility it has for bonding is London dispersion forces. So those are so weak, the vapor pressure for ether is extremely high. In fact, if I take a container of ether to the other side of the room, open it up, then within a few seconds, you would be able to smell it on the other side. That's how volatile it is. It vaporizes very quickly. And in addition to that, it's extremely flammable. Right, so don't light a match if you try that. Okay, so there's an explanation of vapor pressure. And vapor pressure does increase significantly with temperature. because you're overcoming those bonds that hold the liquid to the surface, hold the atoms to the surface of the liquid, or the molecules to the surface of the liquid. And this is a response curve for temperature versus vapor pressure for various compounds. Notice water is very low, and it reaches 1 atmosphere, 760 torr, at 100 degrees, whereas ethanol reaches its boiling point at only 78.4 degrees, and ether will boil at 34.6 degrees. Right. So if you want ether to boil, put a glove on that's resistant to ether, and then submerge your hand in it, and you'll make it boil. Because what's body temperature? 37 degrees centigrade, which is higher than the boiling point of ether. Actually, don't do that. Because especially not in a closed space, you'll pass out. Okay. Now, how do we relate this amount of energy that's required to vaporize a liquid to its vapor pressure? Well, there were two chemists that came up with this formula. It's called the Clausius-Clapeyron equation. And this version here is the differential equation, which may be useful sometimes, but the integrated equation is this one, and it is much more useful. So here we have the vapor pressure. Here we have the heat of vaporization, which is a measure of how much energy does it take to vaporize a mole of a liquid, right? And that's an indication, the delta H is an indication of how strong is the intermolecular bond. And that's all related to temperature right here, okay? So with that formula, and you can do a set of experiments and graph it, right? Because that looks like y equals mx plus b. It's a straight line, right? Here's your y, where is it? Right here. Here's your slope of the line. Here's your x-axis, and there's your y-intercept. So if you graph the data at different temperatures, pressure against temperatures, then you can determine what the delta H is for that experiment. And maybe some of your homework problems and review document will have examples of that as well. Okay, so there's just another example. We'll not go through that. Let's see. There's another form of the Clausius-Clapeyron, right? So if you, with this one, you can, rather than graph it, you just need to make two measurements. The vapor pressure at temperature 1 and the vapor pressure at temperature 2, then you can solve it for whichever unknown you're interested in. Right. And notice here the universal gas constant is the one with energy in it. Okay, there's an example. We're not going to go through that because I'm already over.
The changes that occur as energy is added to a solid can be summarized by a heating curve. This section of the graph represents water in the solid state, or ice. Starting at a low temperature, we see that the temperature rises as energy is added. In this region, the added energy increases the motions of the solid molecules, but the molecular motion remains centered on a fixed position. This section of the graph represents the melting of ice to form liquid water. When the curve abruptly changes slope to 0, the solid is melting. Here, all the added energy is used to overcome the intermolecular forces holding the water molecules together in the solid structure, allowing the water molecules to move around more in the liquid state. There is no further change in temperature until all the solid is converted to liquid. This section of the graph represents water in the liquid state. Further addition of energy causes the water molecules to move around faster, increasing their kinetic energy. The water molecules are attracted to one another by hydrogen bonds, but the rigid structure characteristic of ice is no longer present. Water is more dense than ice because the structure is more mobile and the cavities present in ice are no longer maintained. This section of the graph represents the vaporization of water. In this area, the temperature remains constant again, in spite of the addition of energy. The added energy is used to overcome the intermolecular forces between the molecules in the liquid, changing the molecules into the gaseous state. The temperature remains constant until all the liquid evaporates. This section of the graph represents water in the gaseous state, or steam. Addition of energy raises the temperature because the kinetic energy of the molecules is being increased and the molecules are moving around more rapidly. The molecules in the gaseous state are far apart and relatively independent of one another.
Okay. So, what we're seeing is in these lines that have a slope, a positive slope, you have a single phase where the temperature is increasing, energy is being added, and it's adding to the internal energy of the phase, but it's not breaking the bonds that hold that phase together. So once you get to this point, now you have both solid and liquid together, and any further addition of energy causes the bonds, the intermolecular bonds, to break. So you will have both solid and liquid together. That's why when we did experiments where we needed to have a constant temperature, if you have ice and water both in the container at the same time, you know that the temperature is near 0 degrees centigrade, because that's when it's the melting point of water, and it's going to stay there as long as you've got both phases together. But after the solid is all melted, then the temperature is indeterminate. Well, you can't easily tell without measuring it. So as long as you got the liquid and you're adding energy, then you're going to get a rise in temperature of that liquid. Then when you get to this point, you're vaporizing liquid and gas, and liquid and gas are together. And then once you've got all gas, you can superheat your steam. So that's one way to look at a phase change, a phase diagram. It's not the only way, but it's a good place to start. Okay, so we're going to have to do a concept check. Which would you predict would be larger for a given substance, the heat of vaporization or the heat of fusion? Remember that they're each a measure of how much energy it takes to change phase from for fusion from solid to liquid, and then from vaporization from liquid to gas. So which one should be larger? Vaporization, of course, right? Because going from solid to liquid, you still have some intermolecular forces holding the substance together. But when you go from a liquid to a gas, you are breaking those bonds completely, and there's virtually nothing left of the bond. So the heat of vaporization is always higher than the heat of fusion. Now, another way to represent a phase, another phase diagram, takes advantage of equilibrium lines. That is, with temperature and pressure. Let's go to the next one. Here we go. So with temperature and pressure, at any given pressure or temperature, you have an equilibrium that can be established between two phases. And you can draw a line. For instance, you could draw a line here, So that would be an equilibrium line between solid and liquid. Right? So at this temperature and that pressure, you have both solid and liquid at the same time. If you draw, say, for our diagram there, if you draw one like that, then you've got gas over here. So at that temperature and that pressure, you have gas and liquid in equilibrium. Or if you draw one like this, you could have an equilibrium between solid and gas at that pressure and temperature, whichever one you choose. Okay. Those are the phase equilibrium lines. We have two other areas, points and areas on this graph that are of interest. One is the triple point, and the other is the critical temperature. Okay, this is the triple point. At that pressure and that temperature only, you can have all three phases together. That's the triple point. When you get out here to a high enough temperature and pressure, you reach an area where that equilibrium line stops. And anything beyond, out in this region, you can't tell the difference between liquid and gas. It's still fluid, right? It flows, as all gases and all liquids do, but there's no way to tell, to see the difference between liquid and gas. And there are videos. I didn't put one in the PowerPoints. There are videos that can show you. You can see the two phases, liquid and gas, and then they gradually increase the temperature and video it, and all of a sudden, the line between them disappears. They've exceeded the critical point. So you've heard in popular literature the discussion of supercritical fluids or supercritical fluid extractions, which is one way to get decaffeinated coffee. If you use a gas that you have pressurized and heated to the right point, you can create a supercritical fluid and use it to extract selectively from a substance. We used to do this with carbon dioxide. The nice thing about it is it's a benign substance for extracting things from living tissues. It will extract everything of interest from a cell, and the cell will not be disrupted. It'll just go right through the membrane, pull it out, and then once you've got it extracted, how do you get your extractants? Well, you just decrease the pressure and your carbon dioxide is, and you got your pure substance left behind. Okay, so that's a phase diagram, and most phase diagrams will have this solid liquid line tilted that way. There are a few exceptions, and water is one of them. Water tilts back the other way. So what does that mean? Well, if you start at a temperature here, and for any substance across that line, as you increase the pressure, you go from gas straight to solid. Okay? Or if you go the other direction, solid to gas, of course, that's sublimation. Or if you go the other way, if you increase temperature from solid to liquid, that's melting. Or if you down here and you increase the temperature, you go from liquid to gas, that's vaporization. Right? Or if you go backwards, that's condensation. Or if you go backwards, that's, let's see, it was melting, and then solidification. And then this way would be sublimation, going from solid to gas. Going the other way, from gas to solid, when you actually make dry ice, for instance, would be called deposition. So I think there's another, well, there's an example of water. For water, if at a given temperature, if you increase the pressure high enough, you go from solid to liquid. So for the longest time, I thought that that was a plausible explanation for why ice skates work so well. Because you take all of your mass and put it on a very small area of ice, which increases the local pressure on ice to the point that it converts from solid to liquid. And then you're floating on that lubricating water. But subsequent experiments have proven that wrong. Those skates are actually right on solid ice. And the reason you can go at such high speeds on ice is because the coefficient of friction between steel and solid water, ice, is very, very low. Okay, so there's the phase diagram. Now, concept check. As you, I got to answer the door, excuse me. Come on. Be quiet, I got to finish. One of my dogs. As you increase the molecular forces, what happens to each of the following? Okay? So if you increase the force of attraction in a liquid, what happens to the boiling point? It takes more energy, so the boiling point should go up. Increase temperature. Okay? If you increase the forces holding molecules together, what should happen to the viscosity? The viscosity should increase. It does not flow as well. Okay? Surface tension. Increase those forces, you get an increase in surface tension. That residual pull at the surface of the liquid that we talked about. Or I talked about. The enthalpy of fusion, that is enthalpy, how much heat does it take to melt a solid? Well, as those forces increase, it takes more heat. Freezing point, going from solid to liquid or liquid to solid at that point, if the forces are much higher, it takes more energy or a higher temperature to melt. Vapor pressure. If the forces are stronger, then the vapor pressure should decrease because the forces of attraction in the liquid are holding those molecules more tenaciously. They do not vaporize easily. So this is the one that actually decreases. Vapor pressure decreases with increasing intermolecular force. And the heat of vaporization is like the heat of fusion. It would also increase with increasing molecular forces. So it turns out the only one that decreases as the intermolecular forces increase is the vapor pressure. Oh, that's it. So let me stop the share. And let's see. That's all I have. Unless you have comments or questions. You want to, okay, you want to be sure. And last time I checked, Steffi was the only one that was registered in homework. So you want to get in there quick as possible because time's a wasting.
I purchased it from the bookstore, and it actually sent me an email to a shipping link. I don't know if where I bought it that way, it's shipping me a hard copy of the book, or if they're mailing me the code. Or
Oh.
because I whenever I first emailed you asking if Cengage was the right thing,
Yeah.
I purchased it from the bookstore then.
Okay,
I don't know.
at the New River bookstore?
Yeah.
Okay. It should have been as Cengage Unlimited. Did you buy Cengage Unlimited? Or did
Yeah,
you
it
buy,
was
you bought the book?
it was a scene gauge link. Hold on, I'll go. What
Okay.
it may be doing is they may mail a code or something instead of sending it through email.
Well, they may email it to you.
Yeah.
They wouldn't snail mail it to you. They should send you you should have access to the code really quickly. If you don't, send me the particulars. You know, if you have a screenshot of what you bought or something, so that I can contact the sales rep and see if you got the right thing, because they can take they can take your ISBN number, and tell you if you bought the right product to give you access to the OWL homework. Okay. Do that.
Okay, I'll send you an email.
Yeah, do that as quick as you can so we can get this resolved.
Okay.
Okay. Everything else good? All right.
Yep. Yeah, Tuesday.
See you Tuesday if I don't hear from you before then. Let's see. Recording.